The summer of 1921 was brutally hot. In Boston, a brilliant physician named George Minot was starving to death. He survived on a meager diet, clinging to life as a skeletal figure. Far away in a dirty Toronto laboratory, a young surgeon found himself covered in dog blood. Frederick Banting was an unlikely savior. He was not a brilliant scientist and had even failed out of his first university program. He trained as a battlefield medic during the war, before abandoning a struggling rural practice to chase a crazy idea. Yet this failing surgeon had just achieved the impossible. He proved a cure for diabetes existed inside the pancreas. This discovery had the potential to save countless lives. The discovery had a fatal flaw. His extraction method was useless for actual patients. It was impossible to scale up for industrial production. The cure existed, but it could not reach the millions of people who were actively dying. He could not save a single human life. I am Professor Jim Brody. To understand insulin, we must look at a strange idea Banting had at 2 in the morning. Everyone knew the pancreas held the key to curing diabetes. Banting understood a basic biochemical trap. If you ground up a healthy pancreas, the digestive enzymes of the organ would act like molecular scissors and instantly destroy the delicate insulin. The problem was that the proteases produced by the green cells destroyed all the insulin contained within the purple cells when you ground up the pancreas. How could you separate the purple from the green? Banting read an article describing this medical anomaly. When the pancreatic duct contained these stones, kind of like kidney stones, it blocked off the duct, and that led to the green cells all dying, and the purple cells remained, suggesting that this could be used to separate the insulin from the proteases. Banting's 2 a.m. idea was simply to do the surgery and tie off this duct, reproducing the effect that these stones had. That would leave the purple insulin-producing cells all alone and easily separated from the green protease-producing cells. He took his idea to the University of Toronto and Professor John J.R. MacLeod. At first, MacLeod dismissed the amateur surgeon. He eventually relented and gave Banting 10 dogs, a dirty lab space, and a student assistant named Charles Best. MacLeod then left on a long summer vacation. Banting and Best went to work in the sweltering heat. The work was brutal, and many dogs died of sepsis from the crude surgical conditions. They eventually perfected the surgery. The best proof was a white terrier mix named Marjorie. They removed her pancreas to induce diabetes and then injected her with their crude extract. Marjorie survived for an unprecedented 70 days. Banting had proven that insulin was real. A physiological proof of concept is very different from an industrial reality. Think about the logistics of this surgical method. To get enough insulin to keep one dog alive, Banting had to operate on a second dog. He had to tie off its ducts and feed it for 6 weeks while its internal organs died. And then, only then, could he harvest the tiny remnant. Scaling this to humans was impossible. North America alone had over 1 million people with diabetes. They were all hanging on to life, and thousands died every day. To keep them alive, you would need tens of millions of dogs. Even using livestock was absurd. The idea of armies of surgeons operating on millions of cows and waiting 6 weeks before slaughter made no logistical or financial sense. Banting's surgical method was a dead end. Banting knew he had hit a wall. The supply of extract from dogs was a drop in the ocean compared to the demand. He remembered from his farm childhood that fetal calves in slaughterhouses had not yet fully developed their digestive enzyme. He thought they could skip the surgeries entirely. They could just extract insulin directly from the pancreases of unborn calves before the destructive enzymes became active. They tested this on a dying boy. On January 11, 1922, they gave an extract made from fetal cow pancreases to Leonard Thompson. The 14-year-old boy was dying in a diabetic coma. The extract was crude. They injected a massive amount of thick brown muck into his body. The experiment failed completely. The fetal extract was just too toxic. The fetal calf pancreas lacked active enzymes to destroy the insulin, but it was still packed with other non-human proteins and cellular debris. When this murky fluid entered Leonard Thompson, his immune system recognized the foreign material as a massive threat. The immune system mounted a huge inflammatory response. This resulted in a painful swollen pocket of dead white blood cells and fluid known as an abscess. The boy's blood sugar barely moved, and the toxicity of the extract caused his condition to decline. This was ultimately a chemical purification problem. Leonard Thompson was still dying. The surgical approach had failed. The fetal calf approach had failed. If humanity was going to survive diabetes, they had to abandon surgery and turn to pure chemistry. Professor McLeod saw the failure clearly. He knew that the surgery was the wrong tool. They needed chemistry. The University of Toronto team brought in a young biochemist named James Collip to pursue this alternative path. Collip had a clear directive. He needed to figure out how to chemically separate the delicate insulin from the enzymes using normal adult pancreases straight from the slaughterhouse. Collip started by using cold temperatures. He kept the fresh pancreases completely chilled. This dramatically slowed the destructive action of the enzyme. He then used a chemical technique known as alcohol fractionation. Proteins dissolve differently in alcohol. Collip discovered that different proteins have different solubility threshold. He found that if you blend the pancreas into a solution of exactly 85% alcohol, many of the toxic proteins will solidify and fall out of solution, where they can be filtered out. The real breakthrough came next. Collip took the remaining fluid and increased the alcohol concentration to 90%. At 90%, more proteins fell out of solution, including the insulin, and it could get to be a fairly pure compound. The remaining toxins stayed suspended in the fluid. Temperature controls the speed of biology. James Collip's first insight was that he could lower the temperature and reduce the activity of those proteases. So at room temperature, when you grind up the pancreas, these proteases destroy the insulin. Instead, he put them in ice, and that just prevented the destruction of the insulin. Here's how Collip did the purification. First, he added 80% alcohol. Collip realized different proteins will condense at different concentrations of alcohol. When he added this alcohol, some of the proteins would fall out of solution, and then he could filter those out. And so in this case, you could see the insulin went through the filter paper and it ends up down here with these other yellow ones, where these other proteins are up here. Of course, he doesn't know where the insulin is, so what does he have to do? He has to test both of these. He puts them back in solution. The only test he had was that he knew that insulin would lower blood sugar. So he would inject this solution into a rabbit and test whether or not rabbits' blood sugar went up or down. Here's a chart for blood sugar levels for humans. For rabbits, it's similar. There's a normal range. Now, when you eat, it tends to push your blood sugar higher. Your body naturally responds by releasing insulin, which pushes it lower. What Collip did was just inject insulin into these rabbits. So he pushed them down into this region. What he noticed, some of those rabbits would have seizures, loss of consciousness. He also learned that he could recover these rabbits by injecting glucose and bringing it back into the normal range. So after this, he had a semi-purified solution of insulin, but it wasn't perfectly pure. So his next step was to take 90% alcohol, add it to that solution. You can see here we have both the purple and the green, the purple insulin. The purple insulin falls out of solution, forms a precipitate on the bottom. He can filter that out, and then again, he would have two solutions. And again, of course, he wouldn't know which one had the insulin, but he could do the same rabbit test. After that, he had pretty purified insulin. He could put it back into solution, do a final test on the rabbit, and that was what was injected into patients. Collip delivered a practical reality. With his highly purified alcohol extract, they injected Leonard Thompson a second time on January 23, 1922. This time, the boy woke up. His blood sugar dropped to normal levels, and the toxic ketones vanished from his urine. The medical team went down the hospital ward. They injected the extract and woke up comatose children one by one. They brought them back from the edge of death. It was a stunning moment in the history of medicine. Chemistry was also about to fail. One ward of patients was safe, but there were many others. This was not a drug you only take once. These people needed more insulin or they would quickly return to their comatose states. Word of the miracle drug spread rapidly. The University of Toronto tried to scale up the 90% alcohol purification method from their small glass laboratory beakers to massive industrial manufacturing vats. When they did that, the insulin vanished. The massive vats produced absolute nothing at the end. There was no insulin where it was supposed to be. Collip checked his meticulous notes. He confirmed that every single chemical step was identical to his small laboratory experiments. The industrial vats purification system remained empty. Patients who had just been saved began sliding back into comas as the local supply of insulin inexplicably dried up. The University of Toronto had the cure, but they were fundamentally incapable. of manufacturing. Academia could not solve an industrial crisis. The researchers realized that they had to partner with a manufacturing titan to save these children. Professor McLeod contacted a pioneering pharmaceutical company in Indiana named Eli Lilly. Next time, we will uncover the mystery of the vanishing insulin. We will meet a young industrial chemist named George Walton. He realized that the answer was not in the alcohol purification, but in the electrical charge of the molecule and the newly discovered pH. The race to apply the recently discovered properties of pH and its effect on solubility begins.